So the question I've been tasked with is, the climate has always changed. What makes this different? So let's go way back. So when the Earth kind of formed and had early climate, it was in that Goldilocks zone, or not too hot, not too cold. So it could sustain water, it could sustain life. The exact temperature has been set through time, through things like the composition of the atmosphere, the cycle, the orbit of the Earth in relation to the sun, the output of the sun, etc. And I'm going to show a few graphs, and they look technical, but hopefully they're not that hard to understand. So on the far left is a plot going back through time. This is just from the previous IPCC assessment report, counting backwards in time from 0 through to 60 million years ago. And this is the composition of the atmosphere in terms of carbon dioxide concentration in parts per million. From scale goes from 100, 200, and so on. And going far back into the past, using our natural climate records through things like boron, phytoplankton, things like that were around at the time that produce a natural climate record in rock and so on, and ice cores and so on. We can see that the carbon dioxide concentration used to be much higher than it is today. There's quite a range of uncertainty because these records are not perfect, but there was obviously times in the distant past that were much warmer than they are today. Going to the much more recent kind of past, only the last 800,000 years, we can see carbon dioxide has varied between about 180 and 280, or less than 300 for the last 800,000 years. And in the last 2,000 years, this time counting forwards from 0 to the year 2000, it was relatively stable and then has been shooting up. And as everyone probably knows, through that period, global average temperature and carbon dioxide concentrations have really been locked together because they are linked through processes including so for example, the solar cycles start a trend, and the CO2 is kind of a feedback on that, on those solar cycles, creating slowly in and rapidly out of ice ages through all of that time. So out of the last ice age, this kind of line on the last graph, the global average temperature went up by about 4 degrees, and the carbon dioxide concentration went up about 100 parts per million in about 10,000 years. Recently, we've had 1 to 1.1 degrees of global average temperature rise since about 1850, and 125 ppm of CO2 in just over 150 years. So you can see that rate of change is very different, more than 50 times faster. So this is one version of the very famous global average temperature series since 1850 through to today, including this so-called slowdown period, which when you put it in perspective doesn't look like very much. And you can see marking off our kind of progression past half a degree, hitting 1 degree and heading up towards 1.5 and 2 degrees in a matter of hundreds of years rather than thousands of years. And carbon dioxide measured at Cape Grim, which is a very important air monitoring station globally, steadily rising, breaking 400 parts per million in 2017. And this is the fastest rate estimated for about 66 million years. Recent climate changes in not only temperature, not only CO2, but other greenhouse gases. This plot on the left goes from 1900 through to the year 2020, showing CO2 concentrations hitting that 400 parts per million kind of milestone. If you get all the other greenhouse gases, long-lived ones such as methane, nitrous oxide, halocarbons, etc., turn them into the equivalent of carbon dioxide and put those together, you can see we've just hit another milestone, which is 500 parts per million of carbon dioxide equivalent when you put all those together. This central graph deserves to be one of the most kind of famous graphs when it comes to climate change, which is the amount of energy in the oceans. And this is in the units of zetajoules. And this has been steadily increasing since the 1960s. And the current rate of increase in energy in the ocean, which is where the majority of the extra energy is going, is about the equivalent of about 8 atomic bombs per second of extra energy going into the ocean. And another really important one, which we'll get to in a moment, which is global sea level has been steadily rising, and that rate has been increasing, especially in the last few decades. Since about 1880, there's been over 20 centimetres, almost 25 centimetres as a global average, but that's very different in different places, and we'll get through that a bit more. So Sure, the climate has always changed, it's evolved, we've had some abrupt events in the distant past, life has survived. Long term, if we're wanting to be around as a species on Earth into the thousands and the millions of years in the future, we'll have to cope with these changes and more. But what's different about the current issue with what we're doing? Well, the cause is very different. Rather than these natural causes that are reinforced by climate feedbacks, including through CO2, what we're doing is digging up the geology and emitting it into the air, which is causing a forcing of the climate and pushing it, which is quite different than what's happened in the past. And also rate of change, up to 50 times faster than coming out of the last ice age. So that rate of change is something that's very unusual in the very long-term history of the Earth, and something that is going to be hard for a lot of things to cope with, including human civilization, but also ecosystems and so on.